Hello everyone. Thank you for joining us. I am Ahsan, and this is my partner Uzair. I'm excited to present our work on finding a small vertex cut on distributed networks based on the paper by Jiang and Mukhopadhyay from STOC 23. So, this presentation will explore a novel algorithm for identifying small vertex cuts in distributed systems with applications in network reliability and fault tolerance. So, this is our title slide. We focus on finding smaller cuts. So, let's start. Okay, so our motivation. A vertex cut is a set of vertices that, when removed, splits an undirected graph into at least two components. Our goal is to find a vertex cut of at most size kappa or k. So, to determine if none exists in the congest model, where messages are limited to O of log n bits per round. So, our challenge, this restriction makes efficiency measured in communication rounds a key challenge. In applications, the problem is vital for network reliability, fault tolerance, and designing robust distributed systems. So, why is this hard? The congest model forces us to be clever about communication. So, moving on to the problem statement. So, given a network graph G with n vertices, we need to find a vertex cut of size at most k. The graph is undirected, and we are working in the congest model with O of log n bit messages. So, our aim is to determine if such a cut exists and identify it efficiently in terms of rounds. This whole sets up the technical challenge we are tackling. So, moving on to the related work we found about this paper. So the previous approaches we learned about had certain limitations. The Parter paper from the 2019 worked well for small k values like 1 or 2, but struggled with larger ones. And the Sensor Hilal paper offered approximate solutions which are faster, but they were less precise. So many of the existing methods were impractical for larger degree networks due to high complexity. So where does our work come in? Our work comes in is that our contribution is a randomized algorithm that is efficient for a broader range of k values, bridging the gap between exact and approximate solutions. So moving on to the proposed solution. Our solution uses a randomized approach to balance accuracy and efficiency. We handle two types of cut differently. First of all is unbalanced cuts, where one component is small, and balanced cuts, where components are larger. So we optimize them for distributed systems, leveraging the congest model's constraints. This dual approach is what makes our algorithm versatile. So moving on to the components of the algorithm.
So now I'm going to explain the algorithm components and how the algorithm actually works in a more formal definition. So input of our algorithm is basically an undirected graph with n nodes, and we're also given an integer k. And the goal is to basically find a vertex cut where the number of nodes is at least k or less than k. And the output is will be that vertex cut and the number of nodes and the nodes that are in that cut, or the algorithm will tell us that no such cut exists. And the core idea, as my partner Zardari, Ahsan Zardari just told you, it's basically to handle two types of vertex cuts, unbalanced and balanced. So anytime a cut is applied on a network, the graph is split. And if we have one component which is very small, we can call that an unbalanced graph. And where components are larger, these are balanced graph. So how does the algorithm actually work? The algorithm basically has a couple of subroutines and an approach, a statistical approach to basically find the vertex cut and a merge between approximate approaches and exact approaches. We have a main algorithm that iterates over alpha, which is basically our probability function, and it coordinates all these subroutines to find vertex cut. On an intuitive level, this is basically how it works. We're going to start with checking first for low degree vertices, which basically are vertices that have a lower number of connections, and then we will use random sampling to guess where a cut might be. According to that information, we adjust the sample size via alpha, and then we process it differently based on its density to balance efficiency. In the congest model, each vertex only talks to its neighbors in rounds and sends small messages. So our subroutines are there to manage this communication to avoid congestion and ensuring that the total rounds stay within the upper bound that we have defined. So in this way, the algorithm can cache both balanced cuts and unbalanced cuts through its use of various subroutines. The names of the subroutines are here, like single source local cut subroutine and isolating small cut subroutine. The isolating Small cut subroutine is basically just a BFS function that runs a local flow algorithm to find unbalanced cut inside of a graph component. And the single source local cut subroutine basically checks for global connectivity, and it will basically remove multiple nodes at a time, single nodes, pairs, or triplets even, to find the right vertex cut.
So moving on to complexity analysis. Our goal in the complexity department for algorithm is the time complexity of k to the power of 3 in O d plus square root of n, where d is the graph's diameter. This is a significant improvement for moderate k values, and for practicality purposes compared to prior methods, it's more practical for larger networks thanks to better round complexity. This efficiency is what sets our work apart from the previous method. So moving on to the results. This whole table basically summarizes our results for small k values. Like the Parter work is efficient, but it struggles with larger k values. And for the sensor Hilal, it provides approximations, but our algorithm delivers exact results for k values up to n to the power of a quarter, with complexity k times k to the power 3 with big O d plus square root of n. So this paper, the special case, which is special case for k equal to polygon of n, we achieve near linear complexity solving an open problem. This closes the gap between exact and approximate solutions. So one important thing to note is, however, that exact algorithms for general k to the power greater than 3 were computationally very intensive and impractical for high degree networks. In contrast, our proposed algorithm achieves exact results with significantly improved round complexity. Yeah. So moving on,
So I'm going to discuss how we
implementing this.
implemented the algorithm in the Conjus model. So since the Conjus model is a model that enforces synchronous communication, we can't fully implement the algorithm in that model. So we had to simulate it. And we basically simulated it by doing three things. We enforced a message limit between each round. So this complicated the data exchange process, which made it similar to the Conjus model. And we did a round-based simulation, which basically happens in that model to enforce synchronous communication between network nodes, and we ran through like a debugging process to ensure that networks were interacting with each other. So I'm gonna talk a little bit about the demo. We have implemented a code, the source file for which is available in our repository. Let me show you how that code works basically. We haven't used any large or complicated data sets. We basically defined simple graphs ourselves to see if our algorithm can implement the correct vertex cut. And then we generated graphs based on that cut using Python libraries. And we can see that in our cases, the algorithm correctly identified vertex cuts for our graphs, as we can see in these images. Or it has notified us if such a cut does not exist. So the vertex cut nodes are highlighted here in red. Feel free to check the full source file in our repository, which we will attach in this paper alongside this report. For a performance comparison with previous known vertex cuts algorithm, our is more efficient. The paper that we have used, it has more versatile and more accurate, and also works with multi-node cuts, while previously such algorithms were exponential in scale. These are some of the challenges that we face when implementing this. Multi-node cuts was a huge problem because sometimes we need to remove multiple nodes at a time to identify the correct vertex cut. So this paper basically implemented that by enhancing the single source local cut subroutine. Then there was, of course, sampling variability. Instead of fully random sampling, this paper does deterministic sampling. Sometimes when you have graphs that have a cycle, the paper basically tells you to enforce global connectivity checks after node removal to detect all cuts. And sometimes when the graph is in the form of a star, we have a star graph. The algorithm basically prioritizes high degree nodes to improve detection for small values of k. These are some of the limitations that we faced when implementing this algorithm. When we have large K values, the performance is really effective. And since this is a simulation, we cannot fully implement the real life properties of congestion that may happen during a congest model. And we can also not, we do not know much about how to scale this for large scale actual distributed networks or implement full congestion control as if this were a congest model for real for better efficiency. These are the references. Parter and Sensor are the papers which hold the previous vertex cut approaches that we have. And our paper is the one that was presented in STOC 23. And we have used the libraries NetworkX and Matplotlib to implement our code. That was all for our presentation. Thank you.
Got it.